This is the biggest part of this unit, being able to write chemical equations, chemical reactions. This is also why it is so important to be able to write chemical formulas and names correctly. Because if you can't do that, you're never going to get reactions right. Okay? Because in a chemical reaction, we have to make sure that we have the same amount of stuff on the product side as we have on the reactant side. Okay? The reactants are the things you mix together that react, and the products are the things, obviously, that are produced. Okay? We have to make sure we have the same amount of everything on both sides because we have to obey the law of conservation of mass. If you don't swap and drop an ionic compound correctly, or you don't get the right numbers because you don't remember the prefixes on the molecular compound correct, you'll never get a reaction to balance properly. Okay? Which means you'll break, according to your reaction, the law of conservation of mass, which is one of those universal constants that you can't break. Okay? So naming is crucially important. If you are still struggling with naming and writing formulas, you need to come in and see me for help. Okay? Because you only get better at it through practice and coming in and getting whatever misunderstanding you have straightened out. Okay? So it's crucial that if you are struggling with that, you come in and get some help on it. All right. Signs of a chemical change. That should be a review. What are some signs of a chemical change? Sydney? Okay, so we might get a gas formed. Ooh, that's a terrible color to use. Okay, so we might get a gas forming. All right, and so we might see things like bubbles. What else is evidence that a gas is formed? You might not always see bubbles, but you might sometimes. Okay, you might see a decrease in volume of the solutions that you had previously. It's possible. Okay, what else? Sometimes you can smell it. Sometimes gases are smelly. Okay, and so you might detect a change in odor, all right, as a result of a chemical reaction. And one of the reactions that you're going to do in our reaction lab next week, okay, shows no bubbles, but has an incredibly strong odor. Okay. In fact, if you've ever watched like Olympic weightlifting, you know, they snap those things and those smelling salts and they stick them under the guys' noses to make them crazy before they go out and lift weights. You ever seen that? You got to see it sometime. It's quite cool, actually. Okay. What's in those is essentially like ammonia. When they crack them, it's this horribly, like, when you inhale it, it almost feels like it's burning, but it just gets their adrenaline going, and then they can go out and lift more than they usually do. It's not cheating because it's allowed. But yeah, this you would be essentially, you're going to have a reaction that's going to produce the same gas. Okay, it's a very strong, very distinct odor. It smells like Windex on steroids. Okay, so yes, gas is forming, bubbles, smell. What else? There could be a temperature change. Okay, either up or down. Okay, that indicates that energy is either being absorbed or energy is being given off. Most of the time, reactions give off energy, so they get hotter. Okay, what else? There could be a precipitate formed, or any change in state for that matter. Okay, but precipitates in particular. Definitely color change. That's probably one of the most common ones. Okay. Those are the big ones. Those are the ones that we would really want to watch for as signs of a chemical change. Okay? All right. Learn the types of chemical reactions. There's more than what we're going to go over, but we're going to go over 5 types. Kind of the 5 basic types. Okay? We're going to have to be able to identify each reaction type. They're all distinct. They all have something about them that's different from the others. Okay? And the reason we have to be able to identify them is by late next week, you're going to be asked to predict the products of a chemical reaction only given the reactants. So from the reactants, you're going to have to be able to say, that's a synthesis reaction. I know what happens in a synthesis reaction. The product is going to be this. Okay? Or that's a combustion reaction. I know what the products of a combustion reaction are. Here they are. Right? So you have to be able to identify the type. And again, they are pretty distinct. Okay? Each one of them starts in a specific way. And then lastly, learn how to write them. Okay, basically it's being able to write chemical formulas, okay, the chemical formulas for compounds, and then essentially being able to make sure you have the same amount of everything on both sides. So it's a little bit of like common denominator kind of math, okay, making sure everything is balanced off. Okay, all right, questions on that? Okay. All right, so in a chemical reaction, final products are chemically different than the starting reactants, and that is the key. Okay? In a physical change, they are chemically identical. So, for example, a physical change would be the melting of ice. Okay? When I have ice, what do I have? Water. When I have water, what do I have? It's a trick question. Water. Okay? When I have steam, I still have water. Okay? Yes, I've changed their state. That's a physical change, though, okay? Because I still have the same chemical material I had before. All right? If you crumple up paper, is that a chemical change or a physical change? It's a physical change. Still paper. All I've done is change its shape. Okay? But if you burn paper in a fire, that's chemical. Okay? You started out with whatever hydrocarbon the paper was made out of. Okay? You reacted it with oxygen in the air, and you're left with carbon dioxide, water vapor, and some ash. Okay? It's chemically different than paper and oxygen. Right? It has very different properties, which is why we see these signs when a chemical change occurs, because we now have things that are chemically different. And as we learned in our lab, things that are chemically different have different physical properties. Okay, so we would see things like color changes because now we've produced a new compound and it might be a different color. Okay, or it might be a gas and we might smell it. Okay, or it might not be soluble in water and it forms a precipitate. Or it's a reaction that gives off energy like a campfire. Okay, so all of those things are signs of a chemical change because they indicate that my new products are chemically different from what I started with. Okay, does that make sense to everybody? Okay, so that whole sentence, guys, is pretty important. That's the kind of thing that could be like a multiple choice question on a unit exam or something like that. Okay, so there's generally 5 kinds of reactions in general. There are subtypes of all of these types. We're not going to go into detail on those. That's for like Chem 30. Okay, the first kind is the most basic, a synthesis reaction. Okay, what does synthesis mean? If you synthesize something, you are making it. Yeah, okay? You're building something out of smaller blocks. Okay? Well, that's what's happening in a synthesis reaction. In a synthesis reaction, okay, 2 or more elements react to form a compound. Okay, whether it's ionic or molecular. Okay, so the 2 examples we have here, okay, we can see in this reaction that I'm starting out with magnesium in a solid form. That's what the S in brackets means. You guys won't have to write the states of matter in your reactions. Okay, I'm reacting with oxygen gas, and as a result, I'm getting magnesium oxide. Essentially, if you take magnesium metal and you leave it out in the air, it tarnishes like silver. Okay, and that tarnish is magnesium oxide. It's like a black powder, and you can just wipe it off. Okay, with your fingers, and then you'll have this black stuff on your fingers afterwards. But it is chemically different than both magnesium and oxygen after. Okay, everybody follow there? Okay, what are these big numbers for? Click. Right, it says there's 2 magnesium atoms, there's 1 oxygen molecule, right? This is 2 atoms bonded together, right? Oxygen is one of those special elements. Remember, we highlighted them that day and said we'll talk about them later. Later is now. Okay? Today is later. All right, so it's a molecular element. This is a molecule. Yes, it's both oxygen atoms, but they're still 2 atoms. That's a molecule. So we've got 2 atoms of magnesium, 1 molecule of oxygen, and it's going to make 2 molecules of magnesium oxide. Now, on this side, do I still have 2 atoms of oxygen? Yes, this big 2 says there's 2 molecules of magnesium oxide, and in each magnesium oxide molecule, there's 1 magnesium and 1 oxygen. Okay, so there's 2 of these. That means there's 2 of each of these, and it's balanced. Okay, everybody follow that? Same with this reaction here. Okay, so I've got 2 atoms of potassium. Okay, I'm reacting that with 1 molecule of bromine that contains 2 bromine atoms. Okay, and I'm going to get 2 molecules of potassium bromide. Okay, so there's 1 molecule of potassium bromide. There's another molecule of potassium bromide. I still have the same amount of matter on both sides. Okay, I've got 2 potassiums, 2 potassiums. Okay, 2 bromine, 2 bromine. All right, everybody okay with that? Okay, so I've made sure that that equation is balanced. Okay, so that's synthesis, okay? Only synthesis starts out with 2 elements as its reactants, okay? That's the key identifier for a synthesis reaction, is the only kind of reaction that'll start out with 2 elements reacting with each other, okay? All the other reaction types start a different way. Okay, the opposite of synthesis is to decompose, okay? When you build something up in synthesis, you take the pieces, you put them together. In decomposition, you take the blocks and you pull them apart into the separate pieces. So in a simple decomposition reaction, a single compound breaks down into its constituent elements. It may not always be into exactly elements. It could be into smaller compounds as well. If it's a really large compound, it may just break down into smaller compounds. But it's always going to start out with only one reactant. It's the only reaction that starts that way. Okay? It's the only reaction that isn't actually mixing things together. Okay? Decomposition reaction is just the decomposition of a single compound. So, to make water break down, you actually have to arc electricity through it. Okay? This is actually the process they use to make rocket fuel. Okay? They arc electricity through water and separate it into hydrogen gas and oxygen gas. Okay? 2 both very flammable, very reactive things by themselves. Okay? And that's essentially what they put in the big tank that used to go on the space shuttle, that big orange tank in the middle. Okay? That's what would feed the rocket boosters on the sides. Okay? So what they do is they arc the electricity through, and I get hydrogen gas, which is one of our special elements that always comes as a 2, and oxygen gas, which is another one of our special elements that always comes as a 2. Here's where knowing which ones come as 2s and 4s and 8s becomes important. If I have to predict the products of this reaction, I have to know that this one comes as a 2 and that one comes as a 2, or I won't be able to balance the reaction right. And I won't be saying what actually happens either. Oxygen never hangs out by itself. Okay? Neither does hydrogen. Okay, is this reaction balanced? How many hydrogens do I have on this side? 4, 2 times 2, right? There's 2 water molecules according to this big 2 here, and each water molecule has 2 hydrogens in it. Are there 4 over here? Okay, how many oxygen atoms over here? 2, right? Because every water molecule has 1, and there are 2 water molecules. Okay, over here, there's 2 oxygen atoms. Okay, that's what we do when we're balancing a reaction. Okay, another example would be if we had nitrogen tri-iodide breaking down or decomposing. So nitrogen tri-iodide looks like this. The nitrogen atom is here in the middle. Okay, the iodine atoms surround it. When it breaks down, I get 1 molecule of nitrogen. So that accounts for these 2 nitrogen atoms. Okay, and I get 3 molecules of iodine. Okay, which accounts for the 1, 2, 3, 4, 5, 6 atoms of iodine. Okay. This kind of reaction most often involves special elements. Okay, it most often breaks down into nonmetals that are molecular elements. Okay, questions on the decomposition reaction? Okay, remember, its key identifying feature is the only reaction that starts with only one reactant. Okay, now this was to highlight again the special elements in case you missed them that day. Okay, nitrogen comes as a 2, oxygen comes as a 2, fluorine, chlorine, bromine, iodine, astatine. Okay, and hydrogen all come as 2s. Phosphorus comes as a 4. Sulfur is an 8 when they are by themselves. Okay, those are the special molecular elements. Okay, so other than hydrogen, they're all together over there. Okay, other than hydrogen. Okay, anybody need that one anymore? Okay, next one is combustion reactions. There's some easy things about combustion reactions, and then there's some tougher things about combustion reactions. The easy thing about combustion reactions is the products are always carbon dioxide and water. Always. Okay? A combustion reaction always produces carbon dioxide and water. Okay? The tricky thing about combustion reactions is they have special rules for balancing. Okay? They're balanced differently than all the other reaction types. Okay? And I haven't really gone into balancing yet, but I will. Okay? But I will talk about the two special balancing rules for combustion reactions here in a second. So what happens in a combustion reaction is, okay, a hydrocarbon, that is a molecular compound containing carbon and hydrogen, reacts with oxygen. In other words, it burns. Okay? Hydrocarbons burn, okay, in the presence of oxygen. And then it always produces these same products, carbon dioxide and water. If combustion is perfect, that's all that gets produced. Okay? Most of the time, combustion isn't perfect. Other gases are usually produced in a combustion process that we don't show here, okay, if it's imperfect combustion. Right? What's a gas that's produced by your car? Carbon monoxide, this stuff. Okay? CO. What's bad about that? It'll kill you. Yeah. Okay? It bonds to hemoglobin. Okay? That's the active ingredient in your red blood cells that's supposed to carry oxygen. If carbon monoxide bonds to the hemoglobin on your red blood cells, it doesn't let go, which means your blood cells can't carry oxygen, and you get sleepy, you fall asleep, and you die. Okay? That's how carbon monoxide kills you. Okay? Your body just starves itself of oxygen because your blood can't carry it anymore. Okay? So that's a very dangerous gas that is produced in imperfect combustion. Okay? Your car is an example of imperfect combustion. It never works perfectly. Okay? Usually the other places we see carbon monoxide get produced is if some gas-powered machine or device is malfunctioning. Okay? A prime example is hot water tanks. Okay? If you have a gas-powered hot water tank and it is malfunctioning, or the ventilation has somehow gotten diverted or plugged, okay, then the gases will back up. Okay, and they'll back up into your house. So it's always a good idea to periodically check the chimney, okay, for your gas appliances, your furnace and your hot water tank. And it's always a good idea to have what in your house? Several carbon monoxide detectors. Okay, okay. You should have several of them in your house at all times. Okay, because if you're asleep when that happens, you won't wake up. Okay, and that's usually what happens. Okay. All right. So carbon monoxide, dangerous gas. It's odorless, colorless. Okay. You can't detect that it's there. Okay. It's a really, really dangerous thing. Okay. But it's not part of the combustion reaction that we're going to talk about. Okay. We're talking about perfect combustion. Now, all hydrocarbons have this setup. They're C something, H something, and they're going to react with O2, with oxygen gas. Okay. This stuff is propane, C3H8, right? So if you have a barbecue, okay, or something like that, it runs on propane. This is the reaction that is powering your barbecue. Okay, your car is powered by this reaction. Okay, what's the active ingredient in gasoline? It's usually written as a number right on the pump. Starts with O. Okay, you guys have not filled up very many cars with gas, have you? It's not fun, although right now the gas is like practically free. It's like only 88 cents a liter. It's really cheap. Okay, okay. The active ingredient in gasoline is called octane. Okay, that's why there's 3 different grades of gasoline. They have different amounts of octane in them. All right, regular gasoline is 87 octane. Okay, I don't know. It's 87, like, I don't know if it's percent or parts per million or whatever. It's just a number. Okay, the mid grade is usually 91 octane, and premium is either 93 or 94 octane. Okay, the more octane that's in it, the hotter it burns and the more power it generates in your car. Don't go thinking that, well, then I should always put premium in my car. Not necessarily. Okay, some vehicles are designed to only burn one grade of fuel. Okay, for example, if I put premium in my truck, it'll mess up all the emission sensors, okay, because it burns hotter, and my truck will think there's something wrong, okay, because all the gases coming out of it are too hot and contain too little oxygen, and it'll think there's something wrong, and my check engine light will come on, then I have to go and pay to have it turned off, okay. So if you always read your owner's manual, really important. Only put the kind of fuel in that it's supposed to have. If your car is only supposed to run on premium, don't put regular in it, okay. It'll be really bad for it because it's designed to have this much of the octane in it. Okay? All right. Now I said there were some special rules for balancing a combustion reaction. Two special rules that only apply to combustion reactions. And that is, or those are, sorry, plural. Okay? The first rule, you'll have to write this down because it's not in your notes. We balance them alphabetically. It is the only reaction where that is true. In all other reactions, you start with the largest number first, okay? But in combustion reactions, you always balance alphabetically. And the second rule, we call the rule of two, okay? Okay? If you have an even number of carbons, you start your balancing with a 2. Okay? And I'll show you what I mean, because to balance octane, you have to do that. Okay? So again, these only apply to combustion reactions. Okay? Don't try and apply these balancing rules to balance other kinds of reactions. They'll only work with combustion reactions. Okay? Anyone need those rules, or can I scroll back up? Okay, so if I want to balance this reaction, which is the reaction that goes on in all internal combustion engines, okay, I start with carbon because I'm supposed to balance alphabetically. There are an even number of carbons. 8's an even number. So I start my balancing with a 2. Okay? So how many carbons do I have on the reactants, that's the left side of the reaction? 16. Okay? 2 times 8 is 16. So I've got to go over here, find out where my carbons are, and make sure that there are 16 of them. Okay, now my carbons are balanced. I have the same number of carbon atoms on both sides of the arrow. Okay, products, reactants. Okay, just for clarification, reactants are over here. Okay, products are over here. That's true for all reactions. Okay, what comes next alphabetically, H or O? H. Okay, so I've got how many hydrogens over here? 36. 2 times 18 is 36. Okay, I need to have 36 hydrogens over here. What times 2 will give me 36? 18. Okay. Now I got to balance my oxygens. Here's the problem with balancing oxygens. Oxygen is in 2 different places on this side, and I have to account for all of them. So I start over here. How many oxygens here in the water? 18. How many here? 32, right? 16 times 2 is 32, plus 18 more over here in the water is 50, okay? So we've got 50 oxygens on this side. What times 2 will give me 50? 25. Now my equation is balanced. I have the same number of everything on both sides of the reaction, okay? That's how you balance. I mean, in general, it's how you balance all reactions. You kind of go back and forth and make sure everything is the same number on both sides, okay? But only for combustion do you do it in alphabetical order. Yes, I'm going to do a different kind of reaction, though, not another. Or do you want to see another combustion one? Okay, we'll do one that doesn't require the rule of 2. Okay, so let's, we'll try pentane here. So we'll go C5H12 plus O2 CO2 and water. All right. It does, yes. However, on a test, you can name them according to your molecular naming rules. I will never make it more than 10 on the hydrogen, okay? Because you learn the naming of all the organic compounds in Chem 20, okay? Because they go over the ethanes, ethanes, ethynes, whatever it is. Yeah, there's all these. I don't even remember. It's been so long since I did that. Okay. All right. So we got this one here. There's an odd number of carbons, so I don't need to start with a 2. Okay. Everybody follow me there? So I got 5 carbons here. What do I need to write over here beside carbon dioxide? A 5. Okay. My carbons are balanced. I have 12 hydrogens over here. I need to have 12 over here. What do I write in front of water? 6. 6 times 2 is 12. Now I got to total up all my oxygens. I've got 10 here. 5 times 2 is 10, plus 6 more is 16. What needs to go in front of the oxygen over here to make 16? 8. Okay? Balanced in alphabetical order, back and forth, back and forth. Okay? All right. Everyone okay with the combustion ones? Okay. All right, so we've gone over synthesis, which starts off with 2 elements forming a single compound. We've talked about decomposition, which starts out with a single compound and breaks down into either smaller compounds or elements. And now we've talked about combustion, where a hydrocarbon, a C and an H something, okay, react with oxygen to make carbon dioxide and water. Okay, the last 2 are reactions that only involve ionic compounds. Okay, they are the replacement reactions. Okay, the first kind is single replacement. It's called single replacement because only one thing is getting replaced. In a single replacement reaction, an element, metal or non-metal, is going to react with an ionic compound. Okay? And what's going to be produced is a different element and a new ionic compound. Something is going to switch places with something else. Okay? That's what happens in a single replacement reaction. In this case, the element that I have by itself is copper. So I have a piece of copper metal. Okay? I'm reacting it with silver nitrate. Okay? A solution, that's what AQ means, aqueous, dissolved in water. Okay? So I have a solution of silver nitrate. When these 2 things react, the things that are alike will switch places. So since copper is a metal, it has to replace what? It's got to replace the silver, right? It's got to replace the silver, take its place. So on this side, I get silver, solid silver being produced, and copper nitrate solution. Okay? You always have to end up with an ionic compound in these reactions. If you do it wrong, you'll end up with 2 metals together, or you'll end up with 2 nonmetals together. Okay? Chemistry is old-fashioned. Okay? It doesn't want 2 things alike together. Okay? Everybody follow me there. Okay? So the analogy here is, this guy is by himself, and there's this couple dancing, and he decides he likes her, so he rolls this guy and takes off with his girl, and this guy goes off alone. Okay? Like I said, though, chemistry is old-fashioned. He didn't roll the girl and take off with the guy. Okay? Now, if there's anything wrong with that in real life, that's fine. Okay? But chemistry is old-fashioned. I have to make an ionic compound where I have a metal and a non-metal. Okay? I have to have 2 things that are not the same together to make an ionic compound. Does everybody follow me there? Okay? That's, I know where the analogy breaks down with political correctness, but okay, that's the way chemistry works. Okay? I got to end up with metal, non-metal. Okay? So if instead the reaction looked something like this, let's say it was okay, is that still a single replacement reaction? Starts out with an element and it's reacting with an ionic compound, right? Lithium oxide, lithium's a metal. Okay, so that's an ionic compound. So who is chlorine going to switch places with? Oxygen. It's got to replace the thing that it's like. Okay, so now on this side, what I'll have is lithium chloride And because oxygen is special, O2. All right, is that reaction balanced? It is not. Okay, so now I need to balance it. With reactions other than combustion, we generally start with what's present in the largest number first, except if it's oxygen. Oxygen messes everything up if you try and do it first. Okay, I don't know why, it just always does. Okay, you'll notice that oxygen always ended up being balanced last in the combustion reactions too. Okay, oxygen's just a nice guy, finishes last all the time. Okay, I'm going to start with chlorine. There's 2 of it. Okay, I've got 2 chlorines over here, but how many do I have here? 1. So where should I put a 2? Here. Why can't I put a 2 here? Right, it changes the compound. And if I swapped and dropped this compound, this is a -1, this is a +1. That's the way that compound is supposed to be. Okay? You can't balance a reaction by adding little numbers that aren't supposed to be there. Okay? I see people do it all the time, but you're changing the compound then. All you can do is change the amount of the compound you have. That's what this big 2 does. Okay? Oh, I don't have enough chlorine? I'll just make twice as much of that compound. Okay? Now, I balanced my chlorine by doing that, but what did I do to my lithium? It's actually now balanced, isn't it? Okay? I had 2 over here, always a good sign. Okay? If you put in a number and then you go back and go, hey, now that one works. It's usually a good sign that you did it right. Okay? Now everything should be balanced. I've got 2 chlorines, 2 chlorines. Okay? I've got 2 lithium, 2 lithium. Oh, we got a problem. My oxygen's still not balanced. See how I told you oxygen screws everything up? Even when you do it last, it does. Okay, so I got 2 oxygens over there. What do I need to put here to make oxygen work? Okay, now I got to change some of my other numbers. It's not a big deal. It happens sometimes. How many lithium now? Okay, what do I have to put in front of this? 2. Now it works. Okay, sometimes that happens. You get to the end, you're like, crap, I had everything right. And then you have to go back and fix it all. Okay, it happens. Oh, it'll still work. Once you get going on it and you start going back and forth, there'll be like a lowest common factor that'll work for all of them. Yeah. Okay. We'll work on a whole bunch. You'll see basically every kind of thing that can possibly happen, and you'll see that they all eventually work out. Yeah. Remember, that's part of the reason why we do the swap and drop. Okay? If I don't swap and drop this correctly, I'll never get this reaction to balance because I won't have the right ratio of one thing to another in the compound. So I'll never get the right ratio between them on the products and reactant side. So if you've been working on a reaction, trying to balance it, and you can't make it work, you probably swapped and dropped something incorrectly somewhere along the way. You should go back and check all of those. Okay? That's typically where you've gone wrong if you're having a lot of trouble balancing something. All right, so does everybody follow what happens in a single replacement reaction? Okay, we have these start in a very unique way. They're always one element and one ionic compound. Okay, they always start in that way. Okay, they're the only reaction that starts that way, element and ionic compound. Okay, and remember, you're never going to see molecular compounds in replacement reactions. It's always going to be elements and ionic compounds. All right, the last kind of reaction, double replacement. And while they're kind of the hairiest to balance most of the time, they're actually the easiest ones in terms of predicting the products, okay? Because they're just easy. You just switch the metals, okay? So in this reaction here, I've got calcium chloride reacting with sodium carbonate, okay? On this side, calcium is with carbonate and sodium is with chlorine. So basically all that's happened is the metals have replaced each other. That's why it's double replacement. Both metals get replaced, okay, or they replace each other. Okay? So it'd be like, if you went out dancing with some friends, you're dancing on one song, you're dancing with this person, and then you decide, let's switch partners, and then you're dancing with a new person. You both have new partners now the second time around. Okay, that's what this is like. Okay. Is this reaction balanced? Okay, so sorry, we'll just make a little note here. Always swap metals. Okay, when you're doing that one. So is that reaction balanced? Yes, it is. Okay, there's a 2 over here that makes it all work, but let's just double check. Okay, on this side I've got 2 chlorines. Over here I have 2 chlorines. 2 sodiums over here, 2 sodiums over there. Okay, how many carbonate do I have? That's the trick, right? People always want to say that. Okay, when you look at carbonate, you're like, there's 3 of them. No, carbonate is CO3. There's only 1 carbonate there. Okay, and there's only 1 carbonate over here. Okay, and there's 1 calcium and 1 calcium, so it's already balanced. Okay, all right, let's try a different one. Okay, those are both ionic compounds, agreed? Okay, so to make the products, I'm going to swap the metals. Okay, so that means that on that side, magnesium is going to end up with bromine. Okay, and lithium is going to end up with oxygen, right? Okay, those are both ionic compounds. What have I not done with them? I have not swapped and dropped them. Okay, oxygen's a -2, lithium's a +1, so this is going to be Li2O. Okay, and then bromine's a -1, magnesium's a +2, so this is going to be MgBr2. You must check your swaps and drops before you start balancing a chemical reaction, or it'll never work. Okay? Or it'll work, but it'll be wrong, okay? Which is probably worse. Okay, so I'm going to start with what's present in the largest number. That could be bromine or lithium. It doesn't really matter which one I pick. Okay, I'm going to start with bromine just because that's where my hand is. Okay, so there's how many bromine over here? How many over here? 1. So what needs to go here? Okay, does that make my lithium work out? Okay, 1 oxygen, 1 oxygen, 1 magnesium, 1 magnesium. It's balanced. Okay, it's often just that simple. Awesome. Over here? I did already when I made it, yeah. Yeah, but you would unless I gave it to you. If I give it to you like this, no, I've already done it. If I give it to you in words, then you got to swap and drop. Okay, and oftentimes, guys, that's what you'll get. You'll get a question that says, like, magnesium oxide, be written in words, and then you'll have to write out the whole thing. That's, again, where being able to write your chemical formulas properly is so important. If you don't get this formula right, if you write it like this, you're never going to get the balancing to work. And you'll get the reaction wrong because that's not a real compound. Okay? Generally, the way I mark a reaction is I give you a mark for the reactants. Okay? Sometimes I'll give you a mark each for predicting the products. I'll usually give you a mark then for balancing after that. So a reaction is typically out of about 4 marks. Sometimes it's out of 5. Okay. All right, questions on the double replacement? Okay. When you're writing a chemical equation, okay, and I know all the states of matter have been in all these ones that I've been showing you, but you don't need to worry about those, okay? The G's mean gas, L's mean liquid, AQ means aqueous. It's a solution dissolved in water. S means solid. Okay? So a chemical equation concisely describes a chemical reaction, and it must be balanced, again, because we have to obey the law of conservation of mass. Okay? So this reaction here is already balanced, but let's double check that it's correct. Okay? How many nitrogen do I have over on the reactant side? 3. Okay? How many do I have over here? Okay? I've got 2 here, and I've got 1 more here, which is 3. That's where it gets tricky, okay? Is if an atom shows up in 2 different compounds. You've got to account for all of them, right? Okay, on this side, how many oxygens are there? 7. There's 6 here, 3 times 2, plus 1 more is 7, okay? And over here, 2 times 3 is 6, plus 1 more is 7. So the oxygens are balanced as well. Okay, for hydrogens, there's 2 here, and there's 2 there. The hydrogens are balanced as well. Okay, that would be a trickier balance. If I had asked you to balance that one yourself, that would have been a little trickier. Okay. All right, so a correctly balanced equation is one in which the total number of each kind of atom in the reaction is equal to the total number of the same kind of atom or ion in the products. That's basically from Dalton's atomic theory. Okay, remember he said in a chemical reaction, things combine in simple whole number ratios and atoms aren't changed in a reaction. That's basically, okay, where this idea came from. Okay, and remember that we use coefficients, that's the big numbers, like this and like this, okay, to balance a reaction. We don't change the little numbers, okay, because that changes the material. Okay, we can only change the amount of material, not the materials themselves. Okay, questions there? Okay, what I want you to do is for each of those, I want you to identify what type of reaction it is. I want you to write it out in words, and I want you to balance it. Okay, for right now, since we already did this one, okay, I want you to do the first one and the third one. Okay, just go that far for right now. All right, so on our first one here, okay, we have nitrogen, if we're writing it out in words, okay, nitrogen plus hydrogen, okay, is going to give us nitrogen tri-hydride. Okay, remember that hydrogen is listed second, it's behaving as a non-metal, that's a molecular compound. Okay, all right, now I need to identify the type. What type starts with 2 elements and goes to a single compound? Yeah, synthesis. Okay, I usually just abbreviate it SYN when I'm writing. Okay, their reaction types. Now I need to balance. Okay, I said it's a good idea to start with the thing that's present in the largest number. Okay, and that's still true. Right? I've got 2 hydrogen over here, and I've got 3 over here. What's the lowest common multiple of 2 and 3? 6. Okay, so if I can get 6 on both sides, then it should be balanced. So multiplying this compound by 2 gives me 6, and multiplying this molecule by 3 gives me 6. Okay, and it just so happens that when I do that, it makes my nitrogen balance. I've got 2 over here, and now I've got 2 over there. Okay, so Chloe, you were asking, what do you do if you have like a 2 and a 3? That's what you do. Find the lowest common multiple and then make it work from there. Okay. All right, how many people have done the third one? Okay, what kind of reaction is it? It's a combustion reaction, right? Carbon and hydrogen reacting with oxygen. We said the products of a combustion reaction are always water and carbon dioxide. Okay, so it's a combustion reaction. Okay, CH4, you could say that that's carbon tetrahydride. It's also known as methane, fart gas. Okay. Plus oxygen, okay, gives water, and you can just call it water, don't bother trying to give it a technical name, plus carbon dioxide. Okay, I need to balance this thing now. Combustion reactions have special balancing rules. Balance alphabetically and the rule of 2. Does the rule of 2 apply to this one? How many carbons are there? 1. Is 1 an even number? No. Okay. So I've got 1 carbon, 1 carbon. I've got 4 hydrogens, only 2 over here. What needs to go here? Okay. Now that gives me, on this side, 2 oxygens plus 2 more is 4. So what needs to go here? And we're done. Okay. Now, if you applied the rule of 2 on this, you'd have a 2 here, a 4, a 2, a 2, a 4, a 4, and a 2. Would you get that right? The answer is no, you wouldn't. It's balanced, but it's not in its lowest terms. Okay? When you balance a reaction, it's got to be in its lowest terms. Okay? So if you notice that you've got like 3, 6, 3, 6, you pick numbers that were too big, and you can have 1, 3, 1, 3. Sorry, 1, 2, 1, 2. Sorry. Okay? Everybody follow me there? Okay. Try the rest of these. Give you a few minutes to get ahead of me. This one should have been pretty easy because it was the example for that reaction type that we did. Okay, so what reaction type is it? It's a decomposition reaction. We have a single compound. It's the only reaction that starts that way, breaking down into its two elements. So it's going to be water, breaks down into hydrogen and oxygen. Okay, and you don't have to write like water breaks down, just put the arrow, okay? I don't need like a full proper sentence for a reaction, all right? Now we got to balance it all, okay? Hydrogen's already balanced, but oxygen is not. I need a 2 here to make oxygen balance, which means I need a 2 here to make my hydrogen balance, and now I'm done, okay? That is a decomposition reaction. Okay, how many people are done this one? Okay, let's have a look at that then. So what kind of reaction do I have if I've got an element, in this case a non-metal, reacting with an ionic compound? Single replacement, right? Okay. So this stuff is chlorine. It's reacting with sodium iodide, okay, to make iodine and sodium chloride. Okay, that's what it would look like written out in words. And now I need to balance it. So on this side, with this reaction, I'm going to pick whatever's in the largest number. That could be iodine or chlorine. It doesn't really matter. Okay, so there's 2 chlorines over here. Now there are 2 chlorines over there. But when I do that, it gives me 2 sodiums. So I need to come back here and balance my sodiums with a 2. When I do that, it gives me 2 iodines, and that makes my iodine balance, and I'm done. Okay, now, if this was a fill-in-the-blank question, okay, so there were little, blanks beside these for balancing, what should you put in the blanks beside this one and this one? 1s. That way I know you actually did it, and just didn't stop and didn't know what to do, okay? Because if it's a blank and you leave it blank, I don't know whether it's done and you knew it should have been a 1, or you couldn't finish it and you didn't write anything. So if it's fill in the blank, put 1s. If it's not, you don't need to write anything, okay? What should you never put in front of one of those? A 0, because that means you don't have any of it. And that means somewhere along the way you created matter or destroyed it. And you can't do that. Okay? All right. How many people have done this one? Okay. I will give you a couple more minutes then. Okay. Let's have a look at the second last one here. All right. I've got an ionic compound reacting with another ionic compound to form 2 other ionic compounds. This is a double replacement reaction. Okay, so DR. So this is calcium chloride. It's reacting with sodium carbonate. Okay, that's going to produce calcium carbonate and sodium chloride. Okay, the balancing. What should I balance first? Well, there's only 1 CO3 on each side. Right? And again, but that's a common mistake. That's why I ask. I set you guys up for that. And I'm sorry, Peter, got you that time. Okay? But that's that instinct we have to break. We see this 3 and think it means there's 3 carbonates. It means there's 1 carbonate. Each carbonate has 3 oxygens in it. I'm going to go with either sodium or chlorine. Okay? They're present in the largest number in this reaction. So we'll start with chlorine. It doesn't really matter which one I pick because they go together on the other side. There's 2 chlorines here. Now there are 2 over here, and there's now 2 sodiums over there. So sodium and chlorine are good. Okay? There's 1 carbonate here. There's 1 carbonate here. There's 1 calcium here. There's 1 calcium here. I'm done. I only had to add 1 number for that one. Okay? It looks like it should be more difficult than that, but it's not. Okay? How easy to balance is the last one? Really easy. Guys, if there are no subscript numbers, everything's a 1. There are no subscript numbers in that one. Therefore, everything is a 1. Everything's a 1 on both sides. Okay? You don't have to do anything. That one's already balanced. Okay? Now, you'll notice that I wrote a compound a little differently. What is that? That's water, written as an ionic compound. Okay? Because once in a while it behaves that way. It's still water. You don't have to name it hydrogen hydroxide, although that wouldn't be wrong either. but it is just water. The reason I do it that way is because when we have something that has hydroxide on one side and we form water on the other, it's easier to keep track of where everything goes by writing water as hydrogen hydroxide. If I write water like this, it isn't as easy to keep track of where the hydroxide goes. Okay, so in a replacement reaction, you're often going to write water as HOH just because it's easier to keep track of everything. Good. In certain, again, if there's an exception to a rule in chemistry, it's water. Okay, sometimes we see water behave like that. I'm not saying that water is an ionic compound. It isn't. But when we're doing a replacement reaction, we do sometimes form water, which we shouldn't because we're technically only supposed to form ionic compounds. But water's the exception to that. Sometimes we form water when we have an acid-base neutralization reaction. Okay? Anytime you have an acid and a base, you get water and some form of salt as your products, always. Okay? You always get water and a salt when a base and an acid react with each other. Okay? Because you got to get something that's neutral. Water's neutral. Okay? So we have KCl, our salt, and water. Okay? When you add, when you do this reaction, you just went ooh, but you've been doing this since like grade 3. Vinegar and baking soda. Okay? This is an acid-base reaction, right? When you do this, this is the H plus, this is the minus over here, this is the plus, and this is the minus, but it forms this weird thing. It makes carbon dioxide gas. It's a weird, that's where all the bubbles come from, okay? And then it forms water, and it forms a salt, and that salt is acetate, it's sodium acetate. That's the stuff they put on salt and vinegar chips to make them taste like vinegar, but not be soggy. It's good, but that's the salt that they use, sodium acetate, because it tastes like vinegar. Awesome. Just water. It would be dihydrogen oxide. Again, it's a molecular compound. That's why water is just the exception to everything, right? If there's going to be something that's problematic, it's going to be water. Yeah. You could. Yep, it would be right. I mean, really, I couldn't mark you wrong for writing hydrogen monoxide, or sorry, dihydrogen monoxide. I couldn't mark you wrong for hydrogen hydroxide. Yeah, that one, I mean, hydrogen oxide, it's not an ionic compound, right? So that would probably be about the only one that I would say I wouldn't accept. But there's lots of acceptable names for water, but water's easy, right? Just write water. All right, is that stuff making sense, guys? Okay, let's look at balancing this one. Looks like it's going to be like really hairy, except that it's already balanced. Okay, this is acetate. How many of it are there? 1. How many over here? 1. How many sodium here? How many here? How many hydrogens here? Okay, so there's 1 here, right? Okay, and this carbon and this oxygen, they went over here. Agreed? They went into this. Well, this other oxygen that's missing goes here. This hydrogen goes here, and everything's accounted for. It's all ones. It's all balanced. Okay? It's a weird reaction, okay? But it's already balanced. If you wanted to completely neutralize, yes. Yeah. It's not going to be the same mass either. Like, don't get the idea it's the same mass. You'd need to have the same number of molecules, and so you'd have to do what's called stoichiometry, which you no longer learn in Science 10. It's the first thing you learn in Chem 20. And that's where you can figure out, I need this many grams to be this many molecules, and I need this many grams of this stuff to be this many molecules of it. And then you can make stuff work out that way. Yeah. Okay. We'll start that at the end of this unit by going over this equation, the mole equation. That's what we end chemistry with. That's the start of stoic. Okay.